Hello everyone, I'm Kawasaki from the Quantum Phase Electronics Center and Department of Applied Physics in School of Engineering. As you can see on the slide, the work I'm going to talk about today is partly done at Riken, although there are members from the University of Tokyo and Riken, such as some of these renowned professors. It's mainly research done by graduate students from the University of Tokyo who do the heavy lifting. Well, it is in the title. The phrase non-dissipative means doesn't consume energy, and it's a very green term to match spring GX topics. What this kind of device does is that it produces electricity when it is illuminated by light. And research is currently underway to achieve functionality similar to a solar cell, using a completely new principle. Of course, Spring GX is all about green, so we will focus on green functions. And therefore, I would like to talk a little bit about the possibilities of green devices. As you can see here, what we're going to talk about today is the principle of shift current, which many of you are probably hearing about for the first time. A solar cell is a photoelectric conversion that works on the classical principle. But here I would like to talk about a very interesting phenomenon that uses wave interference to generate energy. Without wasting any of it, the objective is to create a highly efficient solar cell. And I am, of course, in the middle of the road. There is the possibility that this can also be used as a very good light detector, and I would like to talk about that. Okay, so what I mean by electricity flowing through a solid is that if you have a conductor and you plug it into an outlet, and electric current flows through it. This kind of phenomenon is generally called Ohm's current. You all know Ohm's law, where heat is generated when a current passes through a resistor. Ohm's law says that if you know the voltage of the outlet or the voltage of the battery, you can find the current once the resistance is determined. But this always produces heat when the current is applied and is dissipative. The heat generation is actively used in electric heaters like this, or even in the case you do not really want a device to generate heat. For instance, the semiconductor chip in your smartphone generates heat and warms up the phone, which is called joule heat. This means such devices are not green and are dissipative when the current flows. If you ask what kind of electric currents do not consume any energy, there are actually two kinds of electric currents that do not, number 2 and number 3 here. Number 2 is called superconductive current, which I'm sure some of you know about in the literature. But a phenomenon was discovered more than 100 years ago, that when a certain material is cooled to a very low temperature, its resistance becomes zero. It's possible even at slightly higher temperatures. Such materials, when kept cold, can float on top of magnets, and this superconductivity that floats on top of magnets can be used in the linear motor cars that are currently digging tunnels. In other words, it would be possible to make a train float and run. Unfortunately, such superconducting currents with zero resistance are limited to low temperatures, and there are many barriers to their practical use. The third current that I'm going to talk about today is called a topological electron current. This is possible in principle at room temperature and has been demonstrated at room temperature. It is non-dissipative, with no energy consumption upon current flowing. What is the principle behind this? You might imagine electrons moving as particles, but electrons also have properties as waves, and the interference effect of waves allows the current carrying information or energy to run through the solid. The example has actually been known as a phenomenon since about the 1970s. One of the examples is called quantum Hall effect, which was discovered in 1970. Another example is the shift current that is the topic of today, generating electrical current upon light illumination. Shift currents have been attracting a lot of attention in the last 10 years. And this shift current is what we want to talk about today. This is exactly why we are also going to talk about quantum effects. which are a very important phenomenon in the world of physics. However, I am sure you are familiar with some examples. So here are 4 typical examples. If you're a student familiar with physics, you know this. For example, there's a certain barrier for an electron. In classical equality, when an electron flies in, it hits the wall and does not slip through the wall. But in the quantum world, when the thickness of this wall is very thin, about the wavelength of a wave, then there is a certain probability that electrons can escape due to the tunneling effect. Or, when electrons are confined in a very small space, the wave nature of the electrons appears. And it is possible to obtain only a state with an integer number of waves. This is an example from physics. And in chemistry, a hydrogen atom has a nucleus with plus charge in the middle, and electrons are spinning around the nucleus. When the electrons are spinning around, they do not consume energy. And when they spin around, the wave nature of the electrons comes into play again. The orbits of the 3 electron waves are drawn here. Only the integer states are allowed for the spinning orbits of the electrons. This is called quantization, and we know this for sure. If we put 2 hydrogen atoms side by side, their wave-like properties will cause interference. This is like dropping a pebble on the surface of water. If you drop 2 pebbles on the surface of water, when waves propagate in all directions from where the pebbles fell, the 2 waves are superimposed, and there are areas where the waves are strengthened or weakened. But if you use the interference well, you can get 2 hydrogen atoms to chemically bond together to form a molecule of hydrogen. This is what we learn about chemistry in the quantum world. In fact, quantum effects are known to occur not only in the microscopic world, but also in the macroscopic world. And there are 2 representative quantum effects, both involving non-dissipative electron flows. One is superconductivity. As I mentioned earlier about the linear motor cars, if you reduce a substance to lower and lower temperatures, and this is 100 Kelvin, so if you cool it down to about 1/3 of room temperature, it's there, what happens when the resistance becomes 0 below this temperature is that when you apply a magnetic field, the electrons are spinning around this magnetic flux tip. And this is almost the same thing that happens with hydrogen atoms. But this effect causes the superconductor to float above the magnet. On the other hand, the quantum Hall effect is a bit difficult to explain, but when we look at the resistance, we see that the resistance oscillates with the magnetic field. But when we apply a magnetic field introduced at the red area vertically to a semiconductor, the electrons spin around the magnetic flux in orbits equivalent to orbit 3. But when the magnetic field is increased, these orbits become smaller and smaller, and eventually the electrons fall into orbit 2. When a wave goes around the orbit 1, that's where it matches up in a special state, and this is a quantum effect called the quantum Hall effect, as used in the exercise called the standard of resistance. And it is macroscopic because it can be seen even if the sample size is 1 centimeter, not angstroms or nanometers. The same effect is totally visible, which is why it is said to be macroscopic. I think what I'm going to talk about today is the photovoltaic version of the quantum Hall effect. I'd like to review photovoltaics for a moment. And then I'd like to talk about solar cells. Solar cells are used in calculators, and solar panels are being used to generate electricity all over the world. So, what is the principle of these solar cells? The principle of solar cells is that when light is shown on a certain material called a semiconductor, power can be extracted through 2 processes. One is that semiconductors have a gap of about 1 volt between where electrons are and where electrons are not, which is called the forbidden band. If the energy of the light is greater than 1 volt, an electron that enters this bottom is knocked up by the light with a pop and jumps up. The vacancies of electrons that have been created by the excitation are called holes. and they tend to have a positive charge against the electrons' nature of having a negative charge. We need to separate the electrons and the holes, with the electrons on the left side and the holes on the right side. The method on the left side is utilized in classical solar cells, and the one on the right side is based on the principle of shift current. A solar cell is a semiconductor material which contains a junction connecting negative properties and positive properties. We call it a p-n junction. You can create a slide in the semiconductor and spatially separate the electrons, with electrons sliding down to the left and the holes sliding down to the right. So we can spatially separate them. An alternate method in this shift current, called bulk photovoltaics, this semiconductor itself has a positive and negative bias. That is what we use. Even without the slippage, just the effect of the imbalance between the left and the right. The electrons are kicked out to the left, and the holes are kicked out to the right. This kind of situation arises and energy is extracted. This is how the principle is used. Now, this photovoltaic solar cell principle is actually a phenomenon. It's been known for a very long time, and the first one is the classic one that everybody is using. The principle of solar cells was discovered in the 1800s, and Dr. Einstein, who you may know well, won the Nobel Prize for the photoelectric effect, which is also very closely related to the principle of the solar cell. And the power is going out from the lead wire attached as a battery. The first demonstration of silicon solar cells that could actually generate electricity was done at Bell Laboratories in the US by a company called Sharp in 1962, more than 60 years ago. They released a radio with a solar cell attached to it. However, the bulk photovoltaic effect, or shift current that I talked about, uses quantum mechanical wave interference. The phenomenon of the new 21st century solar cell is also a phenomenon that was actually discovered more than 60 years ago. And the principle was not understood for 60 years. Only recently, in 2012, a theoretical interpretation was made that this must be the principle. It was a colleague of mine who elucidated it in its entirety. Dr. Nagaosa discovered this principle in 2016, and it has been a huge field of research for the past few years. It's become a lively field of research. One example of semiconductors with broken inversion symmetry is ferroelectricity, which may be difficult to understand for those with a liberal arts background, but when there is a crystal like this, titanium is used in the ferroelectric material called barium titanate. Titanium and oxygen are mutually displaced, and titanium is displaced upward in the inverted one. So the one with a negative charge and the one with a positive charge are mutually displaced, and the crystal itself has this positive and negative polarization. This positive and negative polarization. Furthermore, the downward polarization and the rightward polarization are allowed to be switched freely between two different states. This is actually a built-in electric state, a ferroelectric memory, like this that you all have. There is a card like this, and inside of this card, they rewrite information using wireless communication. For example, they know that 2,500 yen is left inside of the card. This is the reason why this principle is used to store this information. To go in reverse, it can be inverted by applying the electric voltage from the outward direction. But actually, this crystal has positive and negative charges. So when it is inverted, the plus and minus charges are in opposite directions. The red dot just moved in the external circuit, which means that a current flows through it. This current is being conducted by voltage, but what I'm going to talk about today is the principle of conducting the current by light. As I mentioned earlier, the phenomenon of the shift current has been understood for 60 years. But the principle has not been understood for a long time, and this is an example of the erroneous interpretation that people thought before they understood it. In the polarized semiconductor I mentioned earlier, the left side is positive and the right side is negative. And in this state, there's a very steep slope in the crystal. However, when the crystal is exposed to air, if there are positive and negative charges on the surface of the crystal, Ions with the opposite side will be drawn to the surface, and the positive and negative charges will cancel each other out. And the slide in the crystal will not be inclined at all. This is the perfect ideal state, and in the real world, if you stay in this kind of in-between state, we all believed that this crystal with broken inversion symmetry and polarization would have a slip of about 1 volt. When the light hits, the electrons go to the left. Then why can't they flow to the right? We all thought that, but when we look at the phenomenon, we found that the left and right voltages were mysteriously 100 times larger than the typical semiconductor voltages of 1 volt. The fact that a voltage about 100 times larger is generated is the reason why this absolutely could not be explained. This is why everyone was baffled. The more troubling example is this one, which is an experiment from the 1970s. As I mentioned earlier, it was done by shining light on a semiconductor with a typical electric polarization. But, you know, your sunglasses or your ski goggles, for example, are called polarized glasses. So there's a reason why there's a vertical and a horizontal polarization. The change of light can be easily divided into vertical and horizontal polarization. But we have found a phenomenon where the current in a semiconductor flows in the opposite direction just by changing the direction of the light polarization, and this can never be explained by a slide in a crystal. The positive charge and the negative charge are spatially biased in such a way that the positive charge is up and the negative charge is down, so everyone understood that there is an electric polarization. But this was still very problematic. We want to know the number of plus and minus charges. The polarization of the positive and negative charges could be determined by X-rays or electron microscopy. But when the polarization was calculated at the determined position, it was about half of the polarization value actually observed. This is a difficulty that we could not explain. This is the polarization of this atom. And if we try to explain this experimental value of 26, we have to consider a larger charge than that, which is +7 for titanium and -5 for oxygen, which should be +4 and -2 respectively for the maximum value. This is why we were all very confused, because we couldn't explain such a value. The figure below shows what we found out at that time. This ionic displacement is for the core electrons. In fact, the outermost electrons of an atom, called valence electrons, which are involved in chemical bonding, sometimes take counteractions to these electrons. The distribution of electrons in a crystal cannot be expressed by such a simple equation. This is very difficult and is done using a special function, which I will not explain here. I won't explain in detail, but the point is that the core electrons close to the nucleus have some shift from center, and as a result, the polarization created by the valence electrons, which are far away from the nucleus, and the polarization of the electrons are combined, and when we observe it and shine light on it, we find that the polarization on this side is actually the source of the power generation. This is what we have recently discovered. This is a little bit difficult, so please think of this as a slide for physics students and bear with me for just one slide. The blue line and the red line above are the energy levels when light shines. The light shines on the lower state of the electrons in the semiconductor. The electron in this blue line is popped up by the energy of the light. Then the red line and the blue line intersect here. This is the interpretation invented by Dr. Nagaosa and Dr. Morimoto, in which the interference of waves, called the wave function, occurs, and the current value can be written in terms of the interference light of these waves. If you think about it spatially, when the positive and the negative charges are in a line, when light hits them, the electrons jump from the element with the larger electronegativity to the element with the smaller electronegativity. So the electrons jump a little bit to the left. This is actually the principle of the shifting current, which is exactly the same formula as the Josephson junction of superconductivity, which is the interference effect of electrons. And when electrons are kicked by light, they split to the left and the whole to the right. This is what I mean by this, so please bear with me on this slide for those with a bit of a physics background. And if I were to draw a diagram of what I just said, it would look something like this. As I mentioned earlier, a crystal with an electric polarization has an electric polarization that is negative on the top and positive on the bottom. This kind of polarization is present throughout the crystal. And this kind of polarization is the downward-facing electric polarization. And if you quickly apply a pulse of voltage to it, you can flip this polarization, and when it flips, a current flows through the external circuit to compensate for it. This is called displacement current. This has been known for a long time, but it was not until the 21st century that it was discovered that this is actually caused by the interference effect of the electron waves in the crystal. If you shine a light on this polarized crystal, the moment the light hits it, the electrons in the positive light will be divided into upper and lower parts in this figure, and the current corresponding to that amount will flow through the external circuit. If you put a resistor outside, that should do the work, where the energy of the light will be converted into electrical energy, which is the same principle as solar cells. Let me give you an example of a little experiment. This is SBSI, composed of elements called antimony, this is an element called sulfur, and this is an element called iodine. This is a one-dimensional crystal called SBSI, as shown here. When crystals are made, needle-like crystals of less than 1 millimeter are formed in a flash. And these needles are pulled out like this, and samples are made to stimulate electricity. And we test how much electricity flows. This material has been known since the 1960s to be a ferroelectric material. That is, a crystal with spontaneous polarization. And it was already known in the 1960s that at 20 degrees Celsius, it's a perfectly polarized crystal, and below 20 degrees Celsius, this kind of electric bias occurs. These are the properties of these crystals. It's been known for a long time that when an electrode is attached and light is shown on it, an electric current flows through it, but the principle of this phenomenon was not well understood. When you calculate the electronic state, you can see how much the band gap is. Theoretically, it's clear what kind of polarization the material has. That is the most recent interpretation. This picture below shows how the antimony with positive properties and the antimony with negative properties are tilted in this needle-like crystal. The way it looks is very similar to this orange polarization P. I will now show you how this pink current flows when the polarization is generated by this orange P. The most surprising thing is that this needle is attached to a platinum electrode, and when the temperature is changed, the resistance of SBSI is very low when the temperature is high, but when the temperature is lowered, this resistance becomes very high. The current that spontaneously flows when illuminated by light hardly changes, but the slope of this current voltage characteristic changes, which means at lower temperature, the resistance becomes larger, and when the resistance becomes larger, the voltage of the solar cell generated at both ends of the crystal also becomes larger. The voltage of 70 volts at low temperatures is coming from one crystal. This is totally different from the property of about 1 volt that characterizes semiconductors. That is what I found out. If you do this circuit in an equivalent circuit, you end up finding that the larger this resistance is, the larger the voltage that is generated, and this is an ordinary solar cell. We have come to understand that this is a completely different principle from the silicon cells that generate 1 volt. So it turns out that it's a very different principle. In the case of a classical sliding tail solar cell like the one I just described, it is known that it is very easy to obtain an electric current if the electrode that draws electrons and the electrode that draws holes are made of different metals. In the new principle of the shift current, it was found that the use of platinum for both electrodes actually facilitates the removal of current. And this is a completely different principle. That is, in a classical p-n junction solar cell, If the electrons or the electrode goes to the left, it is easy to extract electrons. It was very important to make an electrode where it's easy to extract the holes. If the electrode holes go to the right, but this is originally a hole-type semiconductor, so it is also all about extracting whatever is incoming by making both platinum. With that platinum, it is very convenient for the holes. We found that it has those properties. This means that it is completely different from the principles of conventional classical solar cells. This is a very important thing to say, because in conventional solar cells, this side has a lot of electrons called N-type. It's a solar cell, but for this hole, there are an awful lot of them that don't get caught outside by the electrons and slip to this side. The same is true for the electrons. On this side, there are a huge number of holes, and those that recombine with the electrons are the ones who slip through. In other words, how well this slip-through is accounted for has been a decisive factor in increasing the efficiency of solar cells. But the shift-current solar cell does not need to worry about such things at all, because only holes are left, so there's no need to worry about recombination at all. This is a whole new thing, because you don't have to worry about it at all. This is the reason why this is considered to be a completely new principle of solar cells. There are various kinds of defects and impurities that degrade the properties of solar cells. There is no such thing in this world as a perfect crystal. They're the cause of that, which we talked about earlier. In the classical slide method, as I mentioned earlier, the electrons go down the slide to the left, but before they go to the right, the defects in the solar cell cause the electrons and the holes to recombine, and the energy cannot be extracted from the cell. The shift current uses the interference effect of quantum mechanical waves, so there is no fear of recombination at all. And the holes of the electrons will be split into left and right without any slippage. In other words, defect or no defect, the interference effect works anyway. The electrons and holes flow without any concern for such things. This is the kind of principle that we are working on, and we conducted an experiment to verify it. I took about 8 crystals that are good crystals and 8 crystals that are bad crystals. The vertical axis shows the degree of electricity flow in total darkness. Conductivity is high for crystals full of defects. However, little electricity flows through them when the crystals have almost no defects. I've collected similar crystals, but there are some defects, and the degree to which electricity flows through them can differ by about 8 orders of magnitude. Of course, the resistance is low because electricity flows easily. And this one has high resistance, but when light is shown on it, a photocurrent of the same magnitude as the one with high resistance is generated. The magnitude is in the order of picoamperes. This contradicts our conventional understanding with regular solar cells, that the ones that have a lot of defects don't produce enough electricity, and that only perfect crystals without defects generate electricity. In our case, even if there is a defect, it's not a problem at all to extract the power. This is convenient. Written here is the property called dark conductivity, and the one on the right is a poorly made semiconductor that often gets high conductivity, because it has many defects. Conversely, on the left, this semiconductor does not easily conduct electricity because it is perfect. However, the current value that flows outward when this is exposed to light is exactly the same regardless of the quality of the semiconductor, and exactly the same amount of electricity is being extracted. This breaks the common sense understanding of semiconductors and means that electricity can be extracted regardless of defects or not. These are classic electrons and holes sliding down the slippery slope. Those that slip through can be extracted as power. In contrast to the common sense interpretation, defective or not, as long as light hits it, it generates electricity. This is a very simple demonstration that this is already a completely new principle. Now, I would like to consider the efficiency of solar cells based on this principle. When considering solar cells, it is said that there is a certain limit to the energy that can be generated by a certain semiconductor. And this was developed by 2 great physics professors, Professor Shockley and Professor Queisser. Dr. Shockley, who won the Nobel Prize for inventing the transistor, is the one who invented the limit theory. This means that he and Dr. Cuiser also showed the limits of the solar cell. In the lower left-hand corner, there is, as you all know, the sunlight spectrum. The rainbow-colored part here is visible to the human eye at around 400 or 700 nanometers. So the sunlight contains a lot of longer wavelengths of the UV spectrum. The highest efficiency for solar cells made of semiconductors from sunlight of various wavelengths can be calculated for each semiconductor. And it is known that a semiconductor such as gallium arsenide, which has a property of about 1.5 volts, has a maximum efficiency of about 35%. As the strength of the bonding, also known as the band gap of the semiconductor, becomes stronger, efficiency goes down, and then as the bonding strength gets weaker, the efficiency goes up. This is the principle here, but if you have a semiconductor with a small band gap where the coupling is weak, you can absorb the blue light and get this voltage, VOC. So while these electrons are falling down to here below, this energy is lost. The voltage limit is in semiconductors with a small band gap and weak coupling. While the coupling is strong, when the red light hits, the red light has less energy. So the electrons cannot go up, which means that the red light cannot be absorbed, so this is a loss of energy. This is the limit of the generated current. That is, the limit of these semiconductor solar cell principles is that the efficiency is about 35% at the very limit of the voltage limit and the current limit. In the best case scenario, and in the instance of very ideal results, it is actually possible to achieve this level of efficiency. Additionally, the circuit diagram of an ordinary solar cell shows that the current that can be drawn from the cell is proportional to the intensity of the light. The voltage is proportional to the properties of the semiconductor, so the energy that can be extracted out of the cell. The orange part is determined. However, as I've already explained, in quantum shift current, the current does not change at all when you change the resistance. So it occurs when you increase the resistance of the semiconductor crystal more and more and more. The voltage can be increased not by 1 volt, but by 70 volts or 100 volts or 150 volts and so on. So we think that this could be a very large amount of energy that can be extracted. Based on a very optimistic, very wild, very convenient assumption, we calculated the efficiency of a solar cell using this quantum mechanical shift current. The upper right is the spectrum of the solar energy on the horizontal axis. So it is the spectrum coming from sunlight. And the blue line is the Shockley-Cuiser limit I mentioned earlier. The estimated maximum value from the plot is at around 1.5 volts, which is located at about 30% of the energy of maximum at the battery. However, with a shift current solar cell, where the coupling strength is less than 1 volt, we can calculate an efficiency that can go as high as 80%. I won't go into the details of this, but the point is that it is a quantum mechanical effect. In principle, we can generate a very large voltage by using the interference effect of the wave, where electrons fly from the right to the left of the crystal when light strikes it. By using the shift current in semiconductors with extremely high resistance, and by making the band gap very small, it is possible to far exceed the efficiency of solar cells, the so-called classical solar cells. I'm saying that that kind of thing will be possible. I would like to talk a little bit about one more thing: photodetectors. As I mentioned, the electric current in this principle is caused by the interference effect of waves. And in fact, there are photodetectors. For example, optical sensors. When you are communicating with the US through the internet, laser beams are passing through optical fibers on the bottom of the Pacific Ocean. When we detect such light, we use such a detector to convert it into an electrical signal. Actually, when you use a detector, if the electrons have the characteristics of particles, when the electrons run in this way, The particles, collide with atoms, and the speed of the particles either becomes zero or there is acceleration. This is the so-called thermal noise. In fact, when an electric current flows due to the interference effect of the waves, the particle properties of the electron disappear, and only the properties of the waves are left. So it is possible that there is no such thermal noise. This is a joint research with intensity theorists, but theoretically, using a photodetector with such a shift current means that there is no noise and no thermal noise. And since detection sensitivity is expressed as the ratio of signal strength to noise, this could make for a very sensitive and highly efficient detector. It's gradually becoming clear that such an optical sensor is also possible. This will be the subject of future experimental testing. To summarize what I've said above, I would like to say that the shift current and these sensors are the most important factors for the future. That shift current, the photocurrent due to the interference effect of the new wave, this is what is occurring, and this is actually held in semiconductor crystals. I explained that this current is caused by the interference effect of waves, which makes good use of the polarization, which is a positive property and the bias of the negative property. Now, it'll be very important to search for new materials in which this kind of effect can become very large. And I've tried my best to explain that the current is caused by the quantum effect. In short, the interference effect of waves, but there is no direct evidence yet. We still need an experiment that directly verifies the phenomenon to show that this is an interference effect. At the end of the day, if we want to make this kind of effect really useful, we need to make it into a thin film and make it work when you take the lead wire of such a device. We need to demonstrate that it can generate electricity when it is exposed to actual sunlight, or that it can be converted into an electrical signal when exposed to weak laser light. I think that the research finally will arrive at interesting findings moving forward. Okay then, that's all for my lecture.